In this bonus video, we will solve 6 linear differential equations of higher order, which seems like a lot of work, but you will see that it's not actually that bad. Where do I see them here? Well, let's say this entry. In this entry, I can see the following differential equation. The left-hand side, which I can see here in the column, is equal to this right-hand side, which I can see in the row. So there is indeed 6 equations, and for instance, these 3 equations, they share the same left-hand side. You can also say that these 2 equations share the same right-hand side, which you can see over here. So there is 6 equations. How do we solve them? Well, finding a general solution for a linear differential equation essentially means that we should do 2 stages or 2 steps. First, we will focus on the associated homogeneous equation. And I can see them here. I just imagine that I have 0 here. So let me solve this homogeneous equation that I can see here. And we know a very simple procedure. First, we look at the associated characteristic polynomial, make it equal to 0, find some roots, and so on. So here we go. Lambda cubed minus 4 lambda squared plus 3 lambda. And we are asking, can it get 0? And where? Well, I can factor out 1 lambda out of this. So one characteristic number is 0. And it's a simple one, because I can factor out only 1 lambda. And then there will be a polynomial of degree 2 left. And when I look at it, I can see 2 more characteristic numbers, 1 and 3. So far, so good. You can check that this is indeed a solution. For instance, if I put 1 for lambda, 1 plus 3 is 4, minus 4 is 0. It works. And now, using these lambdas, we can create the homogeneous solution. YHX is a times e to 0, which is just 1, plus b e to x plus c e to 3x. And that's it. That was easy. Now, an interesting feature that we will see here is the switching in the point of view or in the focus. When we are solving the associated homogeneous equation, we don't care what is on the right at all. We just look at the left-hand side of the equation. So this means that this homogeneous solution will be valid for all these equations here in this column. So we actually solved 3 equations right now at the same time. Wonderful. Let's have a look at these other 3 equations. The homogeneous equation has 0 here, and the associated equation is lambda to power 4 plus 9 lambda squared is equal to 0. We can factor out lambda square out of this. So it means there is lambda equal to 0 as a characteristic number, and it has multiplicity 2. It's a double characteristic number. And after we factor out lambda square, there will be lambda square plus 9, and this one has imaginary roots, plus minus 3i. And based on this, we easily write down the homogeneous solution. So for 0, we have just a, e to 0 times x. But because it's a double root, we have to use the second term with a trick where we multiply by x. And then there will be c times cosine of 3x plus d times sine of 3x. That's it. So we have our homogeneous equations prepared, and that was the first stage. Now we pass to the second stage, where we have to find a particular solution, because we are, of course, following the general form y is equal to yp plus yh. And this is already done. It remains to find one particular solution for each equation. And this is where the switching of the point of view comes, because when we are finding a particular solution, we are most likely going to use the guessing method or the method of undetermined coefficients. And there we just look at the right-hand side. We don't look at the left-hand side, at least in the first part of it. So we look at the right-hand side, and we are looking for terms which have exactly this form. It's a product with exponential, sine or cosine, and a polynomial. These are the basic units that we will be looking for. And we can guess the shape of the solution for them. And there is just one simple rule, and the rule says the only 2 important parts are exponentials and sines. The polynomials are not that crucial, but they are important too. But the crucial ones are exponentials, sine, cosines, and they have to be preserved in our guess. the polynomials, they also stay there, but they will be generalized. So that's a very simple rule, but it has some fine points. Let's see. We keep exponential, we keep sign. And the polynomial becomes generalized. So a general polynomial of the same degree, and that's one of the fine points, we have to keep the degree, looks like this. Another fine point is that when we are generalizing the polynomials, they have to be full. We cannot skip any terms. I can see only the linear term here, but if I try to put just ax here, it wouldn't work. And one of the reasons is, well, we remember, or we sort of understand how these methods work, and the idea is that if I substitute this term into my equation, I want this coming out of it, and if I substitute just x, or ax, most likely through those derivatives, there will be also an absolute term coming out, and it would spoil my guess. So I have to give myself freedom to adjust. That's why I need also the lower powers. Okay, so that was one fine point. Polynomials always have to be full in my guess at this stage. The second fine point is that sines and cosines always come in pairs. One without the other doesn't work. And for the same reason, I'm trying to guess a solution. So my idea is that if I take this expression and put it into my equation, I would like this thing to come out of it. But if I put this expression into my differential equation, there are some derivatives. And these derivatives will change sines into cosines and vice versa. So I can expect that when I put it here into this left-hand side, on the output there will be these terms with sines, but also with cosines. I cannot avoid it. So I have to adjust. I have to give myself freedom to somehow fix the input so that the output is the right one. And practically speaking, I will just take this estimate, this guess, and copy it here, but with cosine in place of sine. But here is another fine point. We shouldn't recycle constants, because I want to have a total freedom to adjust individual parts in my guess. So I cannot use A, I cannot use B, I have to use Cx plus D. Because A and B already play some role here, and this role is uniquely determined. So there is little chance that this particular A would also work here. So recycling is good. When you do it at home, it's perfect, but here, recycling, no. Okay, here we go. That's our basic shape of the guess. I preserved the exponentials, I preserved the sines and cosines, they always come in pairs, and the polynomial was generalized. That's the basic rule with some fine points. And we never looked at the left-hand side at this stage. We just look at the shape on the right, and based on this we create our guess, which means that the same shape should appear also here. The left-hand side doesn't really make any influence right now. So I will just copy it carefully. E to 2x sine of 3x plus cx plus d e to 2x cosine 3x. But it was just the first stage, or the first step in our guessing. Now comes the second step, and that's where we finally compare the right-hand side and the left-hand side. So now it's individual, now we are focusing on the whole equation. And we know that there can be some trouble if the behavior of the left-hand side and the behavior of right-hand side overlap, if they are of the same nature. Now, the crucial thing here is that the behavior, the nature of behavior, is coded into exponentials and sines, cosines. So for instance, here I can look, the substance of the right-hand side is given by these two expressions, e to 2x sine 3x. Now, do I see anything like this in my homogeneous solution? And the answer is no. There is e to 3x, but it's something else. So I don't see a match. These two behave in completely different ways, and therefore I do not have to worry about overlaps, about corrections. This would be the right guess. Now, final guess. But there is another way to see it, which is perhaps a little bit more convenient. And this other way involves a special number which would capture the behavior of the right-hand side. So what we typically do is this. I look at the right-hand side, and I create a special number for it, which in this case is 2 plus 3i. Now, there is no magic in it. When we are solving homogeneous equations, we first find lambdas, and based on lambdas, we create the solutions. From real numbers, we create exponentials, and from imaginary numbers, or imaginary parts, we create cosines and sines. And this is the same procedure, we just use it in a reversed direction. So from numbers, normally we create exponentials from real parts, but here we do it the other way around. We see exponential, we get a real part. We see sine cosine, we get the imaginary part of our lambda. So this is really a two-way process, very simple one. You already know it from the homogeneous stage. And now instead of comparing functions, we compare lambdas. Here is 2 plus 3i. Does it have a match anywhere here? And the answer is no. I can see 3, I can see 3i, that's a totally different thing, 2 plus 3i. So there is no match of lambdas, and therefore no correction. Now let's have a look at this particular equation. Left-hand side, right-hand side. I'm comparing either functions or lambdas. So let's try it with lambdas. I can see 2 plus 3i. Do I see it here? And the answer is no. This is not 2 plus 3i, this is just 3i, so that's a different animal. So no overlap, no correction. Again, I could do it on the level of functions. Do I see cosine 3x? Yes, I do, or sine, but there is no exponential here, e to 2x. So again, there is no match. So the behavior of the homogeneous system is different from the behavior of the right-hand side. That's the outside influence. So the way I influence it is different from the way it wants to behave. They don't cross each other. Okay, that would be it. And now there comes another stage in the solution. How does it work? I take my guess, I insert it into the left-hand side, I evaluate all those derivatives, I do all those linear combinations, and I write the outcome in the same form as we see it over here. In two groups, exponential sines, exponential cosines, polynomials, and then I compare it to the right-hand side. But this is just a manual work. There is no reasoning involved in it anymore. And because it's a manual work, we can just leave it to somebody else. We don't have to do it. So essentially, we now have this equation solved. I mean, the important steps are here. So somebody else will just do those manual calculations, figure out the particular solution, and put it together, and they have the general solution. And then we will get it from them. Okay? So 2 equations are finished. That's wonderful. Okay, let's move on. Again, we don't care about the left-hand side. Here we just care about the right-hand side and see what happens. Now I look at it and I know that I will be looking at the behavior of terms, but this is not a proper term because these things are supposed to be multiplied, they are added. So this suggests to me there is actually several terms. I can see them here, I can see them here. So there is one term here, and it has more or less the right form. I can see exponential, I can see sines and cosines hidden here, and I can see a polynomial. That's one term. Then there is another one, and another one. Okay? And there is something called superposition theorem, and that tells me I can handle each part separately, which is wonderful. Let's try the first one. The basic stage when I'm just looking at the shape. I can see e to 3x, that's an exponential. Well, I have to keep it in my guess. E to 3x. I can see no sine and no cosine, and therefore I keep no sine and no cosine in my guess. That was easy, and I don't have to make a second pair. That's even better. Finally, I see polynomial of degree 1. Well, we know what to do. ax plus b. And that's the guess, or the basic guess, for the first term. Let's move to the second one. Okay, I'm going to put plus here, and I'm going to preserve exponentials. I just preserved exponentials that I can see there. I'm going to preserve cosines. How about polynomials? I'm supposed to generalize polynomials. Is there any? And the answer is yes. There is a hidden polynomial. It's actually 1 times cosine. So there is a hidden polynomial of degree 0, and therefore I have to make a guess of degree 0. But I have to be careful. I don't want to recycle constants, so I have to put c here. That's how it is. And again, we can go back to the original idea. How does this guessing method work? We want to take cosine, put it into our equation, pass it through, and make it equal to cosine. This doesn't look very likely. If I just take cosine and put it there, it's very likely that these coefficients will influence it. It will not be just one cosine coming out, but perhaps 5 cosines or something. So I have to put constant here to allow myself to adjust. Anyway, so that's another fine rule, probably the last one, that if you see just a function, then there is one hidden in front of it. It may be tricky for a beginner, but you get used to it quickly. Anyway, another fine rule says they come in pairs, sine cosines. So I have to put d times sine of x here. And now it's a group. That's for the second term. Let's have a look at the third term. I'm going to copy exponentials. I just did. I will copy sines and cosines. I just did. That was nice. And I will generalize the polynomial. It's a polynomial of degree 2. So, okay, what's the last constant? CDE. EX squared plus FX plus G. That's my polynomial of degree 2. And that should be it. Now, you may be wondering, why is there plus? Why not minus? And the answer is, it doesn't matter. If you feel like it, you can easily put minus here, because these constants, they will adjust, whatever sign you put in front of it. So that's another fine rule if you want, or another fine point. Well, that should be it. For each of these 3 parts, we created the corresponding guess. So I'm happy with it. And again, at this stage, we are looking just at the right-hand side, so I can copy it. Here we go. AX plus B, E2, 3x, plus C cosine, plus D sine, plus EX squared plus FX plus G. So that's the basic form of the gas. And now we have to come to the last step when we care about overlaps of behavior. And because there are 3 terms here, I will have to handle each of them separately. Let's have a look at the first one. Again, the polynomial at this stage doesn't really play any role. So I can look at e to 3x. Let's try it with functions first, just out of curiosity whether it works or not. E to 3x. Do I see it here? Oh yeah, e to 3x, just by itself. E to 3x. So I can see an overlap. That's interesting. Will I see it through lambdas? E to 3x is coded by lambda equal to 3. That's the special number for this particular part. Lambda equal to 3, lambda equal to 3, I can see a correction. That's important. So it's e to 3x with a correction. That's important. And since we are at it, let's try it with the other equation. Lambda is equal to 3. Do I see an overlap? No, this is 3i, a totally different animal. So there will be no correction here. After all, I look at the homogeneous behavior and I don't see e to 3x anywhere. So these are totally different animals. Okay, let's have a look at the second group. Cosine. Do I see cosine here? No. How about lambdas? This is actually cosine 1 times x. Lambda is 1 times I, which is just I. Lambda equal to I doesn't have any match, any overlap with characteristic numbers from the left-hand side. So there is no correction here. How about here? Lambda equal to I. Lambda equal to I. I don't see it anywhere, so there is no correction here either. Also, I don't see any cosine here. There's cosine 3x, but that's a different frequency. So that's a different behavior. Okay, last part. Minus x squared plus 13. What is the lambda? Well, I don't see an exponential. And I don't see any sine or cosine here. So lambda is 0. This is actually a special case in a way. And it may be a good idea to simply remember that when you see just a polynomial, then lambda is 0. But for me, it's easy to memorize that, or to understand that the real and imaginary parts are connected to exponential signs or cosines. They indicate presence of exponentials and sines, cosines. So if there is none, it's just zeros. Makes sense to me. Anyway, lambda is 0. Do I see 0? Yes, I see. I have to make a correction here. I have to multiply by x. Okay, let's move to the other equation. Do I see lambda equal to 0? Yes, I can see, and it's a double characteristic number. There has to be a double correction. That's important. So there's just a single correction here, and here it is double. Okay? Now, one of the reasons why people prefer to work with lambdas and not with functions is the polynomial. I see a polynomial. I start looking for polynomial here. Do I see it? The answer is no, so it may be a little bit confusing. Of course, I know that I should be looking for a term without exponential, without sine, cosine. Do I see it here? Yes, this one has no exponential, but it's easier to just write down lambdas. We know how to work with lambdas, so this is an easy step. Lambda 0, I compare. Okay, these are my guesses. Do I want to add anything? Yes, I do. Now comes the manual stage again, when somebody takes this formula and substitutes it here, finds the fourth derivative. Do I feel like taking fourth derivative? No, so definitely somebody will do it for me. But when we are doing this calculation, it pays off to actually multiply out those polynomials. So here, I would actually handle it as e x to the power 4 plus fx cubed plus gx squared. And here, I would prefer to see ex cubed plus fx squared plus gx. This is much easier to handle. And when you see something like that, you may wonder, okay, I talked about fine point about full polynomials. Isn't there a little bit of a polynomial missing? And here, and the answer is no, because this rule about full polynomial refers only to the stage when we are doing the basic guessing. I see a polynomial, I generalize it, full polynomial. I can see a polynomial of degree 2, and I generalize it. So there I have to do full polynomial. But this expression is outcome of some corrections. So this is a totally different story, and it's okay that there is something missing. That's how it should be. So essentially, we solved 2 more equations. Before we pass to the last one, I'll make an important observation. Sometimes people look at this and they say, okay, I actually see 4 parts, because I can see 1 part, 2nd part, 3rd part, and a 4th part. So there will be 1 part, 2nd part, that's the exponential, that's the cosine. And then I can see part which is negative x squared, and I can see part which is 13. So when I'm doing the guessing, where was I? E's. So here I would guess ex squared plus fx plus g, and here I would guess h. Is it possible? The answer is, well, sort of, but it's not a very good idea. Why? Because here we have a certain number of unknowns. 1, 2, 3, 4, 5, 6, 7. And after we substitute into the equation and compare, we get 7 equations. Here we would have 1 extra unknown letter. And that could cause troubles. And also, it's a useless work. After all, you can see that this can be connected just by 1 constant. So if you want to avoid trouble, and it's easy to get into a big trouble, it's better to treat groups as 1 if it's possible. How do I recognize groups which are supposed, or parts which are supposed to be kept as 1? Well, I look at lambdas. Here lambda is 0. Here lambda is 0. Lambdas determine the behavior of the parts, and I can see that these 2 parts have the same behavior. And therefore, it's actually just 1 part. So officially, we play with lambdas only at the 2nd step. First, we do the basic guessing, and then we play with lambdas and we do the corrections, perhaps or not. But it actually pays off to look at lambdas first, so that we can see what's really happening in an expression on the right side of our equation. Here we go, the last one. Let's try to apply our reasoning here. I can see different terms here. I can see the exponential. This one is coded by lambda equal to 1. That was easy. Here is a term which doesn't have exponential, it's only a sign, so this is coded by 3i. That was also easy. Then there is a solitary number 1, that's just a polynomial. No exponential, no sine, cosine, lambda is 0. Here I can see no exponential, it's a cosine 3x, lambda is 3i. And now I look at it and I can see that somebody was trying to, you know, play funny with us, because 3i, 3i, these two terms should be together. And they wrote it intentionally in such a way that perhaps we don't notice and we will make a mistake. But we will not, because we know that we should first look at lambdas. It's a good idea when this is very complicated. Okay, so now we see that there is actually just three terms. There is exponential, there is a polynomial, and these two give us one trig function group, because the frequencies are the same, they belong together. Okay, we are good, we should know how to do the guessing now. Let's see. We preserve the exponential. We preserve the sines and the cosines, okay, and we generalize a polynomial, and that's one of the fine points I've been talking about. There is one hidden in front of the exponential, so there should be a, and the same comes here. Because right now we are doing just the basic guess, we don't care about the left-hand side, just about the right-hand side. Okay, now we can see the sine group, and we should be tempted, or we would be tempted, to something like this. We would do sine of 3x and put a constant in front of it, because again there is one hidden here. But in fact now we know that this sine is connected with cosine, and therefore the proper degree is 1. There should be a polynomial of degree 1. So there should be a bx plus c here. Because sines and cosines, they come in pairs and they do everything the same, because they're like twins. So if one of them has polynomial of degree 1, the other one has to have it too. Okay, here we go. What was the last letter? A, B, C, D. dx plus e, and the other guy is cosine. So that's the proper form for the sines and cosines. And finally, there is this solitary one, which is polynomial of degree 0, just a constant. A, B, C, D, E, F. That's it. Let's copy it. So I don't want to make a mistake. Bx plus c sine plus dx plus e cosine plus f. That's the basic shape, the last one for today. And we are moving to the last stage, corrections, overlaps, matches. Let's take it from the left. Exponential e to x, lambda is equal to 1. Do I see a match here? Lambda equal to 1. I do see a match. Correction here. Do I see lambda equal to 1 here? No. So there is no correction here. And after all, e to x here on the right, and no e to x in the homogeneous solution. So yeah, no overlap in behavior. Second term and the fourth term, they are unit. 3i, do I see 3i here? I see 3, that's not 3i. No correction here. Do I see 3i? Yes, I do. Correction. And I can see sine of 3x here, I can see sine of 3x there. So it's a match of behavior. Finally, 1 with lambda equal to 0. I can see overlap here, and it's a single overlap, just a single correction. I can see 0 here, 0 there, double overlap, double correction. And these are the final forms, and again, now they are ready to be processed. So substitute into the left-hand side, get the output, rearrange it nicely, compare to the right-hand side, do the rest. But again, that's mechanical, that's easy. This was the crucial part. If you make a mistake in the guessing stage, then after passing through and comparing, the equations will not be solvable. You will run into trouble. And that's a sign for you. If you make a guess, you put it into the left-hand side, you work it through, then you compare it with the right-hand side, and there will be some terms missing on the left, so that you cannot create them. Then it's an indication that you made a mistake, in this guessing stage. Most likely you forgot some correction. If you forget a correction, then the term just disappears after passing through. So for instance, if I tried this last guess here and I didn't put x here next to f, then f would just disappear in the left-hand side and I wouldn't have any chance to create 1. And that's a clear-cut sign for me as an experienced solver that I forgot a correction. And that's it. So good luck. See you.